In this lecture, we'll continue our discussion on high-level programming languages, and we'll also take a look at the big picture of programming.
In the last lecture, we gave 4 expectations for programs written in a high-level programming language. Now that we've been introduced to the essentials of writing programs in such a language, it's time to take a look and see how these expectations have been met. The first expectation was that the programmer need not manage the details of the movement of data items within memory or even pay attention to exactly where those items are stored. The programmer's only responsibilities are to declare, or in the case of Python, create, all constants and variables the program will use. So this just involves selecting identifiers to represent the various data items and indicating the data type of each, whether it's in a declaration statement or in Python it would be an assignment statement. Now the identifiers can be descriptive names that relate to the data to the problem that's being solved. Now the data values themselves, they're just moved as necessary within memory by program instructions. And these instructions just simply reference the identifiers. And the programmer doesn't even need to know which specific memory location contains which values, or even what value currently exists in the ALU register. So the concepts of memory address and movement between memory and the ALU, along with trying to generate these constant data values, have disappeared. We don't need to worry about these specific memory addresses. We don't need to worry about the ALU. All we have to worry about is just creating the identifiers and then just assigning values to them. We don't have to worry about moving them around. We don't have to worry about allocating memory. All that, the high-level language takes care of what we need to worry about. And then when it gets converted to the lower-level language, it will take care of addressing all the memory issues. The second expectation is that the programmer can take a macroscopic view of tasks, thinking at a higher level of problem solving. So instead of moving data values here and there and carefully orchestrating the limited operations that are given to us at the machine language or even the assembly language level, the programmer can focus more on writing formulas or in writing these high-level instructions. So like, for example, the programmer can write a formula to compute the circumference of a circle given its radius without having to worry about loading this value and loading this value and adding this to the register and then storing this. They can just worry about writing the formula for that, for computing the circumference. The details themselves are handled somewhere else. So like, just to give another example, think about how we would handle loops or conditions and the loads and the stores and the jumps that we needed to do all that at the assembly language level. We don't have to mess with that at the high level language. We can just create a loop and just say where it starts, where it ends, what's the condition for continuing that loop, or if we have an if statement where we decide where we're going to go somewhere else, we don't have to worry about specifying these specific addresses. The third expectation is that programs written in a high-level language will be portable rather than machine-specific. So program developers will use a variety of different approaches to make their programs portable to different platforms. So for programs that are written in most high-level languages, the program developer will run through the complete translation process. So they're going to use the compiler to create this executable mode, or executable module, I should say. And then that is what's actually given to the user. Program developers very rarely will give source code to the users. That way they can't see what's actually going on inside the program. But they give the executable version of it. So the way this is done is we use the compiler to make it work for specific machines. So what this means is the developer can actually compile a program on any kind of machine as long as there's a compiler for that machine for the language in which the program is written. So what we're saying here is that when we compile our program into machine language, it compiles the language to a specific machine language. So maybe it's specifically for PCs or specifically for Macs. So as long as there's an existing compiler for that target machine, then we can make our programs work for that machine. So like, for example, if we have a program that's written in C++ and the program developer wants to sell his or her program to be used on a variety of computers, well, the developer needs to compile that same program on a PC using a C++ compiler for the PC. And then if it wants to use it on a Mac, it needs to have a C++ compiler for the Mac, and so on. That way it can produce all the various object code variations. So this means that the program itself is independent of the details for any particular machine language because each compiler will take care of that translation. And once we do this, that means the programmers can now distribute that resulting executable instead of having to give out the source code. Even with the availability of the appropriate compiler may not guarantee that a program developed on one type of machine can be compiled on a different type of machine. And this is because each programming language has a certain core of instructions that are considered standard, which means that any respectable compiler for that language must support that core. So we have a set of instructions that must be supported on every single compiler for that language. In fact, there are national and international standard groups such as ANSI, which is the American National Standards Institute, and ISO, which is the International Organization for Standardization. These groups will develop the standards for so many different things. And one of those areas is programming languages. So, compilers are built to support the standards that are approved by ANSI and ISO. Now, the issue is that there are additional features or types of instructions that are not considered a standard part of the language, which means some compilers will support those instructions and other compilers for that language will not. So if a programmer decides to use some of these features, their program may work on particular machines, but it may not work on all of them. So it is a risk for the programmer to write code that is considered non-standard, as you may be able to make it work in one environment, but it may not work at all in the other environment. Newer languages such as Java and C# were developed specifically to run on a variety of hardware platforms without the need for a separate compiler for every single machine. So a compiler for Java or C# would translate the source code program into a very low-level code. In Java, this would be bytecode. So we translate the source code into what we call bytecode. And in C#, we would translate the source code into the Microsoft Intermediate language. Now, the resulting programs are not machine language code for any real machine, but they can be easily translated into any specific machine language. So the program developer only needs one compilation to produce the low-level code, and then they can distribute the resulting program to the various users. So this means the final translation or execution of the low-level code into the machine language of a particular user's machine will be done by a small piece of software on the user's machine. So like for Java, there'll be a bytecode interpreter for Java, which is usually the Java virtual machine, just to give an example. Or even in C#, there's a just-in-time compiler. Now, what about Python? Python is a very different language. I think I already mentioned that. It's very different from all the other languages. Python is actually an interpreted language. It's not a compiled language, which means that it's actually translated from the source code to the object code as we're actually executing it. So every single time we run the Python code, it's translated from the source code to the object code for each line that it's actually run. So we read a line and then we interpret it. We translate it at that point and then we execute it. We go to the next instruction, we read the source code, we then translate it into the object code and then we execute it. And we just keep repeating this. So as a consequence of this, each user's machine would need to have a Python interpreter, but such an interpreter is easily available for pretty much every operating system. It's small, it's quick, and it's free. So it's not really a major issue that every machine would need an interpreter to run Python. But the whole point here is we don't actually compile the Python code. We would read the line, we would translate it as we're executing it, and then we would take care of the execution part of it during the translation process. The last expectation is that programming statements in a high-level language will be closer to natural languages, and they will use standard mathematical notation. Well, high-level languages provide us with statements that give natural implementations of pseudocode instructions. Just to give a couple of examples, we could say something like, while some condition do something, or if some condition is true or false, will do something. So, now, while pseudocode is still somewhat stilted, it's still close to the natural language. We can even use standard mathematical notation such as a plus b and even a greater than b.